all of the water that comes from the subsurface will come to the surface. And this water that is coming up is cold water, is rich in nutrients, is depleted in oxygen, but because it's bringing so much nutrient to the surface, it's going to fuel the food web that happen in their boiling system. So they will start eating by the phytoplankton, they will be consumed by the zooplankton, and then will provide the base of the food webs that will go to higher trophic levels. So for example, we have the marine mammals, we also have the seabird. And this is what it makes so attractive to the people, because at the end, what we are going to be interested in living here beside the weather is because we have a lot of food and we can have a lot of fisheries. And in California, the region where I come from, these are the main important fisheries in California current system. We have a lot of fisheries from ground fish. There are a lot of high migratory species, for example, the tuna and the swordfish and the salmon. And then we have a lot of coastal pelagic. And this coastal pelagic is sardines, anchovies, or squid. Okay, and one important one in the California current system is the sardine. And this is it's a really interesting fisheries, because I'm going to tell you why. It's important in California and also in Monterrey, where I come from. Just remember where I am in the map. So if we look at the time series of the biomass of the sardine in the region, we see that in the 1920s and also the 30s and the 40s, they start to grow up the sardine biomass in the region. And there are quotes that said that the total sardine landings were more than 700,000 tons of sardine, which represented one of the largest season landing of any single species of the fish in the US West Coast. Because of this make a huge development of the fisheries in Monterrey. There were so many sardines that the billion of the tons of the sardines that someone quoted, there are enough sardines in this landing that together, if they laid end to end, would reach from the earth to the moon and back. I don't know who measured this, but I mean, I found like fascinated. Anyway, so this developed at the end a really big sardine factory in Monterrey. And what they do in here, they open many cannery factories. There are the places where the sardines are gone. By the time, or by the 30s and the 40s, there were like around 16 canneries factories in Monterrey. And nothing, they took the sardine, they put it in the cans, and then they export it to the world. And then they named Monterrey the sardine capital of the world. However, of course, everything that is good comes to an end. And then by the 68, there are a quote for a fisherman saying, okay, we caught all of the sardines that we can find in just one night. And the thing that was happening is just a mixture of different stressors. There was a management conflict of the sardines. There were also some overfishing and also some climate variability happening. And by the 1973, they closed the last cannery factory that was happening in Monterrey. If you go now to Monterrey, you can still see in this cannery, in the cannery row, the thing that they made is they made it like a super tourist place. And one of the cannery factories is now the Monterrey Bay Aquarium. That is the main attraction in Monterrey if you go there. But I wanted to come back to the time series of the sardines. So if we continue looking at the time series to more, well, in the 90s, it's not even present time at all. But we can see that there was this period of lower biomass of the sardine, but then this was another peak of the sardine coming up, right? And this was not only found in Monterrey or in California, it was found all around the globe. For example, I have another time series here for the sardine in the Gulf of California that I think you should be familiar with. The part that is most interesting to me is that this peak of higher biomass of the sardines corresponds to some peaks that can be found in some climate index. So my question really is, can we link the climate variability, what were happening to the sardines? Or more broad or general question will be, what are the mechanisms of the ocean variability and the change? And if we can apply this mechanism to the ecosystem variables of the ecosystem fisheries that we are interested. And also, if we understand what are these driving mechanisms, can we predict them? And if we can predict the ocean and the climate at different time and spatial scales, can we apply these questions or can we apply those predictions to the marine ecosystems? So having prediction is great, we need them, but the important part that we need to start is to having a skillful prediction of the ocean. And I'm going to turn maybe here now so I can move a little bit of the stage. And the, oops, did I did that? I think it's the full screen mode. El último. I'm going just to test that this work. Okay. Let's come back. So having prediction is important, but we need a skillful prediction of the ocean or the ecosystem system or the ecosystem variables. Because with this, we can provide decision maker with information that they needed to make or to develop effective ecosystem management strategies. But for me, a reasonable place where we'll want to start to make this ecosystem prediction is if we start having a skillful physical climate and ocean prediction, which then we can connect to different statistical model or mechanistic model of the fisheries or the ecosystem or the species that we are interested on. So we know that we have this time scale. We can have prediction that goes from hours to month, to season, to year, to decade, and also to the century. And if we think about two predictions that are made by hours and days, we can think about weather prediction, right? At least I was checking the weather prediction to come here just to be sure that there was not going to be rain. But in the ocean, this time scale prediction that we have are the tides, and we are really good doing this. We are really good doing tides, and we are really good doing waves. And I'm sure that if any of you do surfing, you are pretty sure that you are checking this prediction. So you know when you are going to have a good ocean. So we are doing also really good, or starting to do really good with seasonal to interannual prediction. And in the California current system, some of this predictability skill come because we understand how the ENSO mechanism work, because it's a really big part of the prediction skill. We are starting to do really well also doing long-term climate projection, because we are having now better climate, global climate models. They are having like more higher resolution. And also we have downscaling techniques where we can reproduce high resolution of the regional ocean. But we have a really big gap in the decade time scale. So we have a gap on how we make this decadal prediction. And this gap is kind of important because at the end of the day, those time scale are the important one for management. Because even if you have a seasonal forecast, the decision makers really need to adapt really fast to this prediction to be able to make a decision about this. And what am I going to show in here today? I'm going to talk about different products that I have been developed through my years as a researcher. And one of them is about doing long-term climate change projection using a climate downscaling system. Then I will show, using a similar downscaling system, I will show some forecast downscaling system for seasonal to interannual forecast. And then the last thing that I'm going to show you is how we can use observational product to understand how the driving mechanism of what are the mechanisms that drive a prediction skill in the decade scales. Okay, so focusing in the two seasonal forecast and the long-term climate change projection, the goal in here is to build a downscaling framework to produce high-resolution seasonal forecasts and climate projection for ecosystem variables in the California current system. And if we think about a downscaling framework, the important component that we have in a downscaling framework are these three. So we start for the global climate models, where we have the couple dynamics and the radiative forcing. And then the output of the global climate model serves as an input of regional model, where we have better resolution so we can resolve the fine scale processes. And then the output of the regional model can serve as an input of ecosystem models, where we can exploit the physical and biogeochemical or biological relationship. But why we really need to downscale these global climate models? The reason is because if we look at the atmosphere components of these models or the ocean component, both of them are really coarse. So they are unable to resolve the coastal well dynamics. They are not able to resolve really well the winds when they are close to the coast. And we are talking here about the scale of in the atmosphere, I don't know, 200 kilometers, 100 kilometers, and 100 kilometers in the ocean. So because of this reason, we really need something else, because this global climate model cannot simulate the climate at local and regional scale. So our hypothesis of all of this work is that increasing the resolution in the regional models that will lead us to a better representation of the coastal and the boiling dynamics. So when we think about, okay, how we do this downscaling system, so there are a lot of questions that someone needs to start thinking if you wanted to solve the problem. These are the three main questions that I found. Which model are we going to use? The other one was which downscaling method, and the other, how do you treat the model bias? So starting by the first question, which models? The system that I'm going to present you, it has three global climate models. They have 100 kilometers in the ocean. They belong to the SIMI-5 archive, and specifically to the high emission scenario. And these three are the name of the three models that I'm going to be showing. And the reason why I pick these three models is because we need to capture, or at least in our case, for the question that we were interested in, we wanted to be sure that we were capturing the range of uncertainty in both the mean and the mean of both the physical and the biogeochemical properties in the California current system. So in this graph, this is just, I didn't put the axis, so I'm sorry, but this is the surface temperature anomalies with respect to the historical period. And in red, we see here the ensemble mean, all of the SIMI-5 models. And then I highlighted the three that I'm going to be using. We have the Hadley model that is here in yellow, that you can see that is projecting most of the warming in the future. Then we have the IPSL that has like a projection that is really similar to the ensemble mean. And then we have the GFDL model that is predicting less warming in the future. And for the regional model, what I'm going to be showing is a regional ocean model system, ROMS, coupled with a biogeochemical model called NEMURO, and it's going to be a 10-kilometer resolution. And another important component of this is you have to be sure that your control run is really good. Control run, I also call it control hindcast, and in my case, it's go from 1980 to 2010. We are updating this to more present, but we wanted to be sure that our control hindcast reproduce the reality as we wanted. And then as a downscaling method, I'm going to be using dynamical downscaling, which is basically using the forcing of what I mentioned before, the forcing of the global model to force the regional models. And also, the last question is, how do you treat the models that come from the global climate models? Because as you know, the models are not perfect. So in this case, I don't want to go so much into detail, but I'm happy to talk about this later. The method that I'm going to use to try to correct the bias of this model is called time variant delta downscaling method. And this is, I'm not going to talk about the method, but I'm going to show the result of applying a bias correcting method. So to show this impact of bias correcting the forcing, I'm showing you here two observations, the mean of two observations in the California current system. We have sea surface temperature on the top and surface chlorophyll at the bottom. And surface chlorophyll, again, proxy for primary productivity. If we take just the original climate model, this is just one of them, and we compute the bias with respect to the observation. Oh, I think I know now what did I do. I am sorry. I pressed too hard. That's why it went outside. Oh, well. Las cosas del directo, ¿no? Quizás debería de haber cogido el rojito. Vale. Vamos a volver a... So we have the bias of the original global climate model. So we can see here, we have a warming bias in the coast, in this region of the central and the southern part of the California current, but we have a little bit of cold bias in the northern part. And then if we compare the surface chlorophyll of the model with respect to observation, we see that the model underestimate the primary productivity. Well, now one can think, I can take the model and just use it to force the regional model, right? Just increasing resolution. But if you just directly do that, this is what you get. So when you don't correct the bias, if you don't correct the forcing of the global climate model, you get an amplification of the bias, at least in the sea surface temperature and in this model, more near the coast. And this bias is higher if we compare with the original global climate output. And also we get way more less surface chlorophyll compared with the parent global climate model. But then if we apply our bias correcting method, and now I'm comparing the bias correcting method with the control run, which I say before that this was truth. We can see that all of the bias global climate model get reduced, and it's also really similar to what we say is a truth. Okay, so with this method, we can capture the changes in the interannual variability. We can also resolve the transient period. And the most important part is that we can correct the bias of the global climate model with respect to the observation. So we have this situation. I hope you are not lost. But we have now 3 downscale projections. Remember that we have 3 global climate models. So we have ROMS EFCL, ROMS IPSL, and ROMS Hadley. And I'm going to show you a little bit of the result. And I'm going to be focusing on the future changes. And I'm going to be showing result that goes from a mean of the last 30 years by the end of the century with respect the historical period. So this is just delta changes, right? Okay, so I'm going to show you the 3 models, but I just wanted to focus in just one of them. In color, we have the delta of the sea surface temperature. Again, the change with respect to the historical period in the future. And then in contour, what I'm showing here is just the mean state of the sea surface temperature during the historical period. And we can see, yeah, we are going to have some warming in the southern part of the California, then we have less warming projected in the northern part. If we look at the other 2 projections, we can see that ROMS IPSL project less warming in the south, more warming in the north, and ROMS Hadley is more or less uniform the warming, more warm water is projected in the northern part. But if you look at right now, the 3 model has different scale. If I put all of them with the same scale, we can really see that this model is less warm than the other 2. But I wanted to, if you see it just like that, you cannot see what are the different spatial changes that I think they are really interesting depending on the projection that you look. And something similar happened with chlorophyll. So if we look at the chlorophyll in the last 30 years of the century, we can see that the ROMS EFCL project an increase, a light increase of the primary productivity in this region of the coast, while ROMS IPSL and ROMS Hadley, both of them project a declining of the primary productivity by the end of the century. But my question again is, this is great, but what is driving this projection that we are seeing? What are the driving upwelling mechanisms in the future? Is it because changes in the nutrients? Is it because changes in the wind? Or is it because changes in the stratification? So to try to answer that, I want to be focusing in a region that goes from the coast to 100 kilometers offshore. This is the beauty of using a regional high resolution model that you can actually, oh, this doesn't work anymore. You can actually resolve what is the coast. Let me just 1 second, I'm going to change this because it doesn't work. There you go. You can actually resolve this region that we have in here. So what I'm going to show you is again anomalies with respect to the historical period. The first variables is we have sea surface temperature, and these are Hohn-Muller diagrams. We have time in the x-axis, and then we have in the y-axis the latitude. So it will go from here to the north of the, I cannot move it, of the California current system. And And we have the three projections, ROMS GFDL, ROMS IPSL, and ROMS Hadley. And we can see that the three projections, they are just telling you that they are going to be a really increasing temperature by the end of the century. But this, the magnitude of these changes is different depending on which model you are, and also some spatial differences. We can look at other variable. Oops. We can look at meridional wind stress, and this is just a proxy for upwelling. And I wanted to point here that every time that you see blue in the meridional wind stress, it means an intensification of the meridional wind stress, which means more upwelling, okay? So more blue, more upwelling. So we can see the ROMS GFDL that is projecting an increasing or intensification of the upwelling by the end of the century. If we move to the ROMS IPSL, we see that the wind are not changing so much, but by the end of the century, we have a strong decadal variability in the wind stress. And then if we focus on the ROMS Hadley, we have this dipole structure where we have intensification of the wind in the north and then a weakening of the wind in the south. And I am sorry, but this pointer is not working that properly. Okay, if we can look at another metric of upwelling, in this case, it's a surface of nitrate. And this will be like a proxy of how rich these upwelling waters are. So we see that one of the projections is in ROMS GFDL and ROMS IPSL. We have an increase of the nitrate by the end of the century, with the difference that the ROMS GFDL, this increase in nitrate happened all along the coast, while in ROMS IPSL just happened in the Southern California bight. And then if we look at ROMS Hadley, we see that the signature is completely the opposite. There is a declining of the nutrients, and also is more intensified by the end of the century. And if we now combine the projection, but we look at in the vertical, right? If we look now like this will give us this will let us understand what are the changes in the productivity. So here we have the integrated chlorophyll as a proxy of productivity in the region. So if we see that there is an increasing of the primary productivity in the central to the north of the domain. And this is because we have a strong upwelling winds, we have intensification, and we are upwelling waters that are rich in nutrients. If we now move to the ROMS Hadley, we see that, again, we have a dipole structure here, but in the region where we have intensification of the upwelling, we are upwelling waters that are poor in nutrients. So the end result is a declining of the primary productivity with respect to the historical period. And then if we look at the ROMS IPSL, the story is a little bit more complicated because all of this strong decadal variability, there is only increase of the nutrient in some region. There is an interplay between the meridional wind stress and also the stratification that at the end is making it that the productivity is declining with respect to the historical period. So with this, I just show you that when we have better resolution of the upwelling dynamics that lead to regional differences in the future changes, that if we bias correcting the forcing prior to downscaling, that is key if we wanted to reduce the historical biases, and also if we wanted to resolve critical processes for the ecosystem. And then I just show you that there are large intermodal differences that they arise in the coastal region, especially for the biogeochemical variables. Okay, then the thing that we did is we take our physical and biogeochemical projection. I lost, oh, here, there you go. We take this output from the high resolution projection and we use them to force different kind of ecosystem models. So this projection has been used, I'm going to try this screen to see if I'm more lucky. This projection has been used to make projection of fish distribution and population that goes from coastal pelagic, high migratory, also ground fish. It has also been used to make projection of aquaculture production in the Southern California bight. Has been also used to study marine protected area, to study the uncertainty and to make ecological decision. And something that I found really cool is they have been used to make social ecological vulnerability assessment of the coastal communities in the California current system. So what am I going to talk today to you about this application are these two. I'm going to come back to my favorite fish, the sardines, and then I will talk about a little bit of the high migratory species. So starting for the sardine, now the maps are going to be a really slightly similar, different, sorry. And in here we have the ensemble mean of the three projection, okay? So this is the ensemble mean of the three models that I show. And this is just the biomass of the sardines. So we can see that during the historical period, we have an increase of the sardine in this region of the coast from the southern part to the central part of the California current system. And then if we look at the future, the thing that we found is that with the time, the sardine biomass is shifting northwards. So it's going to a period of depletion and then a little bit of increasing in this region in the northern part of the domain. And we can see this decadal variability if we look at the time series. So here again, we have in black the ensemble mean, and then in each of the colors is one of the projection. So we can see that we have a period where we have a decrease in the prey availability, and then we have a period where we have increase in recruitment. And this is because the water become more water, and the larvae of the sardines are really happy with this warmer water. But the one thing that I want you to grab the attention is like, see how the uncertainty of the model are. We see two models that they are projecting a double of increase of the sardine in the future. And obviously, following the percent, 50 to 70%, and then we are going to have declining of the sardine biomass in a moment. There you go. So here we have a declining of, or a decrease of the 30 to 70 in the southern part of, and the central part of the California current system. Now we move to the highly migratory species. What I'm going to show here is a combination of the result of many species together. So these are projections in the last 30 years of the century, and this is the comparison with the anomalies with respect to the historical period. Then by the cross, we have the center of gravity of the distribution of the ensemble mean of all of the variables. And we can see that we are going to have some species that they are going to lose the habitat by the end of the century, but we are going to have some species that they are going to gain habitat. We have 6 losing space between 10 to 60%. We have 4 species that are going to move to the northern part of the domain, and they are going to gain habitat by 7 to 60%. But the more important thing in here is all of these species that are going to lose habitat, they are going to be overlapping with some of the most important fisheries in the California current system. And I highlighted in yellow all of these species that are protected in there. So as a summary of this section, I just showed you that some species are going to gain habitat and others are going to lose habitat in response to climate change. There is also going to be like a potential niche overlap between the protected species and also by those that are targeted by the fisheries. And then for the sardines, they are projected to shift northward, but we need to remember that the port of these sardines or any species, the port are still static. So we are going to have some fishing communities that they are going to gain opportunities, but we are also have other communities that are going to lose the livelihood. Okay, so now we are going to change gears and to make a stop. Excuse me. So now I'm going to show you the forecast downscaling system. And this is really similar to the climate projection one. So we start with the global climate forecast. We force a regional ocean forecast. And this is the product that we are making. We have 10-kilometer forecast projection, forecast that they are called retrospective forecast because it's a forecast of the past. And maybe you are wondering, why do you want forecast of the past? Because if you cannot forecast the past, you cannot forecast the future. That's for sure. What we produce is a 12-month forecast, and we have forecasts that are initialized twice per year, one in January and one in July. And we did 3 ensemble members because this is really computational extensive. So we decided to just downscale the 3 ensemble member for a model that reproduce or that give us a really good forecast skill for the California current system. So I don't want to go so much in here because I'm over the time a little bit, but we have two kind of forecasts. The one that we apply a bias correction before doing the forecast, and another one where there is no bias correction. And these are the result. These are sea surface temperature, the mean value of the sea surface temperature in a region that is average from the coast to 1,700 kilometers offshore, and in the bottom is the sea surface temperature anomalies. In green is the forecast where we have the bias correcting of the forcing, and then in yellow are the one that we don't correct the bias. And as you can see, when you correct the bias of this forecast system, we get better prediction of the sea surface temperature. But we don't only do good with the sea surface temperature. Just the main idea in here is like we have significant scale of the variable when we pass this dot line in here. So we have forecast scale of the sea surface temperature from 6 to 7 months in advance. But we have other variables that we have forecast scale. We have bottom temperature that is still good, sea surface high, and also stratification. But we have some variables that we are not doing really good yet in forecast. We have mixed layer depth or of the current at the wind. We only get forecast scale of 1 to 2 months. So this forecast has been already applied to develop some indexes to apply to management during climate extreme, and they have been applied to protecting marine mammals. So this is a summary of the work, but I invite you, all of you, if you wanted to have a better look of them. We have forecast skill that is relatively good for some variables and some bad for others, but we have better forecast skill when we bias correcting the forcing prior to downscaling. Okay, and now finally, the decadal prediction. We are going to come back to see the full North Pacific domain, and one thing that now is new is I'm adding here the Kuroshio-Sayo extension region. So we have this current that will connect later with the North Pacific current. So this is the surface circulation, but in the surface, this circulation is really similar. The problem in the surface is like when there is an anomaly that is generated in the surface, it's going to be generated in the region of the Kuroshio-Sayo extension region. And there has been some work that has been shown that when these anomalies are generated, they start to propagate following the mean circulation of the mean gyre. And this work, they said that this propagation of the anomalies following the mean gyre circulation, it takes 8 to 10 years. Again, think that we are in the surface of the ocean. This is we are in really deep. And then there has been other work that has shown that anomalies that are in the North Pacific current region, they propagate downstream the gyre in the California current system and also in the Gulf of Alaska with a similar time scale to go from 8 to 10 years to go from the North Pacific to the two regions. So the main idea here is like if we have, for example, a variable in the shelf, we have our water mass in here, this water mass is going to be affected by this surface water. So for example, I have it here as a water that are a deep isopycnal at 26.5. And then the idea is this deep water of the isopycnal, it will affect the water properties of the source water that will feed the upwelling in the two systems, the California current and also in the Gulf of Alaska. Okay, so if we come back to the California current system, one variable that is really important for the ecosystem is observation. So what I'm showing in here is a compilation of many observations in the California current system. We can see that in the latest decade, there has been like a strong decline, a strong trend of the observation. But if we really look backward in time and we go to the 50s, if we take all of the time series together, we see that the oxygen has a strong decadal variability. The problem with the oxygen is we don't have observation of oxygen everywhere. So what I did is, okay, I'm going to take a proxy for this oxygen based on subsurface salinity. So I took my subsurface salinity index in the same region where all of these observations were collected, and I developed my index in here. And I can see that with my index, I can capture really well the decadal variability of the oxygen. So then I thought, okay, I have my proxy, so now maybe I can use it to do more large scale studies. So if what I have shown before is true, remember that I have shown that we have anomalies in the North Pacific current region, that they will take 8 to 10 years to arrive to the California current system. I thought, okay, what if we take the anomalies that happen in here 8 to 10 years before to try to predict what is going to happen 10 years later in the California current system? So this is what I did in here. I took subsurface salinity anomalies in the North Pacific current region with these 10 years prior. And I make my forecast, okay? And I did this for my PhD, and back then we didn't have the data. But now, because we are in the future, we can take observation to see if I was right about my forecast. So then I took Argo data that with a surface salinity anomaly, and this is what happened. I was actually pretty good in trying to predict just the California current oxygen, just using the anomalies 8 to 10 years before from the North Pacific current. So this gives us a forecast potential of 8 to 10 years. So my main message from here is that the strong decadal variability in the subsurface dynamics may be exploited to make decadal forecasts of tracers in the California current system. So this is a little bit of the summary of everything. I have showed you that when we bias correcting the global climate forcing prior to downscaling is key to producing a skillful forecast and also for the projection of the regional dynamics. But something that I haven't shown in here, but it's something that we really need to keep thinking about it, is we need a balance between if we wanted to resolve all of the spatial dynamics of your domain versus if you wanted to use all of the available global ensemble of models, meaning how much of the uncertainty you want to be capturing. And then the final point is like basing scale propagation of the subsurface anomalies lead to decadal predictability in the California current upwelling system. And I wanted to come back to my original question. So can we predict marine ecosystem and fisheries? And my answer is yes, but within limit. However, we can get there. So we are really good. We are really solid with seasonal forecasts. We have climate projections that are evolving, but we need to account for the uncertainty. We have decadal mechanisms that can give us some prediction skill, but these decadal predictions are still really challenging to do. But even with all of this, we can still use them to inform the decision makers. And I would like to leave you with a concluding remark that ocean variability and predictability form the basis for ecological predictability, providing the decision makers with the information that they need to develop effective long-term ecosystem management decisions. And with that, I'm happy to take any question. Thank you so much.
Este es el micrófono para todas las preguntas. Ah, ok, muy bien. Bueno, pues muchas gracias, muy interesante. Preguntas, a ver.
Well, that is a good question. It's depending on, we usually use buoyancy frequency, but I don't know, I guess that you can also see mixed layer depth. There is another one that people use. Maybe it's not that good for stratification if you really think about it, or if you look at how separated are the density layers. So that is the one that we use, but we don't, other than buoyancy frequency, I don't have an answer for that. I don't know, maybe you guys use a different, which one do you use? Te diría que las dos. Sí, pues mira lo que... Voy a intentar en español, ¿vale? Si me pierdo, lo vuelvo en inglés. No te lo voy a decir en inglés, no puedo ni empezar. So, we compute something that is called delta, and this delta, with the R, we take the historical period of the global climate model, where we consider historical period, and we make the climatology of that historical period, okay? And then we remove from each time step, we remove from each variable the climatology of the historical period. So with that thing, you have a delta that goes from the beginning of your time series to the end. But in each time, you are removing the historical climatology. Okay, that's one component. That's the delta. Now we have two other components that they don't come from the global models. They comes from the reanalysis that we use to force the models, the regional model. That is why it's so important to have a hindcast that is going to produce what you wanted to produce, because you wanted to be sure that your forcing is realistic. And from that forcing, we took the climatology, okay? We took the historical climatology of the forcing, and also we took the high frequency variability. And in our case, it was 2 weeks high frequency variability. But the problem is, like, you have now a time series that go from 1980 to 2100, and then you have other 2 time series that goes from 1980 to 2020, for example, right? So what you do is, like, the one in the historical period, you repeat it on time. Yes, that will be the natural variability. And what you are doing is, on top of your climate variability and your high frequency, you are imposing the delta that come from the models. That is the way that I did it in this projection, but the way that we are doing it right now is a little bit different, because in the past, the CIMI5 model, they didn't have high frequency, the models. There was not high frequency humidity. There was no high frequency rain. That's why we have to use this method. But the way that we are doing it right now, we still have the delta, as I told you, but then the climatology is the same, but now we don't have the high frequency doesn't come from the historical forcing, it comes from the model, from the global models. Thank you. Sí, sí. Lo estoy haciendo ahora. Sí, no quiero, I don't want to be, exploding there, but yeah, I'm working on that right now too. Yeah. I have seen something similar, but not in the boiling system. In the North Atlantic system, there is also this propagation of the anomalies, and I wanted to do it in the Benguela too, and the Humboldt, but I need time for students or postdocs. Sí. 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 So the thing that we did is, well, the sardines, they only care about sea surface temperature. So if you remember, the 3 models, they were projecting the same, well, no, they were projecting an increase in temperature. So the sign is the same. The magnitude of the change was different. And the interesting thing is that the model that was projecting most of the warming, that was from satellite, one of them, is not the one that is projecting more biomass of the sardines. And this is because the sardines are not linear. So that's my best answer that I can tell you. But at the end, we had the two models that project most of the warming and less of the warming, having similar response of the biomass of the sardine. And then the one that was like in the middle, like similar to the ensemble mean of the global climate model, that was the one projecting an increase of 7 times the sardines. So it's depending of the model, I cannot answer that. Depending on the model that you check, this is going to give you a projection or another. And it's even interesting because right now with this one, you see that there is more upwelling in one of the model and less upwelling in, well, a dipole structure, or more upwelling in the north, that's for sure. More upwelling in the north is projected for sure. But this is for the CIMI 5 model. With the CIMI 6 model, we are seeing different results. Yeah, so we are seeing a weakening of the meridional wind stress, which is, I think, interesting. So I cannot commit to any response. I want to be politically correct. Bueno, los ciclos, voy a empezar diciendo que yo no soy ecologist, so, lo que te voy a decir de la sardina, cógelo así con pinzas, porque no estoy muy segura. Pero las sardinas sí tienen, parece ser que siguen unos ciclos relacionados con bueno, hay algunos trabajos que dicen que están relacionados con el PDO, with the Pacific Decadal Oscillation, pero ahora se está viendo que eso no es así. Así que, porque la PDO también está cambiando. Entonces, no sé muy bien así como, pero sí se ha visto ciclos en el pasado y ahora esos ciclos, si los mira ahora con el PDO, se están rompiendo. Sí. Y ahora se tiene una nueva ola. Entonces, con eso cada vez aumentamos, cada vez encontramos solución. Sí. Y cada vez son más. Entonces, pues poco a poco, sí. Estoy totalmente de acuerdo. Además, vamos como atrasados, porque los CIMI 7, la reunión de los CIMI 7 ya pasa en febrero del año que viene. Entonces ya vamos tarde. Y tenemos tantísima información que yo creo que en algún momento no sabemos cómo utilizarla. Entonces, mi opinión es que como comunidad científica deberíamos de llegar más a acuerdos, en vez de tener 500.000 modelos que hacen 500.000 cosas. ¿Por qué no empezamos a mejorar las cosas que ya tenemos? Porque lo que ahora pasa es que, vale, yo tengo mi CIMI 5 y ahora los CIMI 6 han cambiado el parámetro X de no sé dónde y de no sé qué, y ahora cambia todo. Claro, entonces, compleja la pregunta esa, pero a mí me gustaría mejorar las cosas que ya tenemos, porque siempre tenemos que empezar a hacer nuevo. Una sencilla, porque está muy complicada, ¿eh? Sí. esos tres modelos. Ujú. Bueno, las dos. Nosotros hemos mirado los dos. Cogimos estos tres modelos porque son además los mejores que reproducen el California Current System, pero además yo estaba muy interesada en porque al final lo que tú le vayas a meter en el borde es lo que tú vas a tener de modelo. Claro, entonces, por ejemplo, el Hadley, ahí donde lo veis que tiene tan diferente de los demás, es el que mejor reproduce la circulación en el Pacífico, es el que mejor hace el oxygen minimum zone. Entonces, queríamos algo bueno, que cogiera todo el rango de uncertainty, pero no solo coge el rango, y eso es que no lo he enseñado aquí, pero no solo coge el rango de uncertainty del RCP 8.5, coge también los tres, esos que te he enseñado, como el GFDL es menos caliente, pues coge también un poco de la uncertainty de los emission escenarios. Entonces ahí fuimos bastante estratégicos con los tres modelos, porque queríamos que reprodujeran lo que queremos, porque, bueno, aunque tu California Current no lo hagan súper bien, al menos el borde lo tiene que tener bien, porque si no, y además cómo va a ser la señal en el futuro. Porque tener, por ejemplo, dos modelos que fueran para nosotros, que fueran cercanos al ensemble mean, no tenía ningún sentido, porque nosotros lo que queríamos era ver el rango de uncertainties in the fisheries. Exacto. Entonces depende de cuál es tu pregunta. Si tú de verdad quieres un modelo que funcione, que sea el modelo, es que son un montón de análisis para eso. Sí, 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 lo utilizan. Sí, sí, sí. Solo los modelos esos, bueno, que no hay tiempo, pero los modelos esos en la parte histórica ya están validados. Sí, sí. Eso lo hacen mis compis, los ecólogos, que tienen todo su modelo hecho. Lo que hicimos fue utilizando esa parametrización que ellos habían utilizado para el periodo histórico de Sardines y todo. Ya le enchufamos las nuevas variables de oceanografía. Gracias.